Hello. So far we have seen adjunctions as a way of simplifying calculations or proofs by moving from a complicated category to a simpler category. So we could move from pre-orders, where things are order preserving and a bit tedious, to sets, where things are just functions. But another use of adjunctions is to use them as a guiding principle for what to expect of certain objects. So in this video, I would like to convince you that the plus operation on types, so the thing that says that it's either an A or a B, is an adjoint, and that we can use this to basically describe exactly what this type is, right? So the first thing we have to do is we have to see that this is a functor. And we know that this thing here is a category. Obviously, it's the category of sets that we love. But we also have to see in what sense this thing where you have pairs of sets is a category, right? So the first thing we have to see is that if we look at pairs of things from two different categories, then this is still a category. So if we do that over here, then here I'm claiming that I have C and D and they are categories, then I can form a new category. So I want my objects here to be an object of C and an object of D, right? Because that's what I had in this situation, right? I had an object of set and an object of sets. Okay, so something happened. Okay, and then what should be the morphisms of this category? Well, I have an A and an X and an A prime and an X prime, where A and A primes are objects of C and X prime are objects of D. Well, then I can ask for a pair of morphisms, one from A to A prime and one from X to X prime, right? So morphism in C from A to A prime, and a morphism in D from X to X prime. Okay, and then I need an identity, but I can just do the identity in C as my first component, and the identity in D as my second component, right? And to compose things, if I have an F and a G, and an F prime and a G prime, then I can just compose these things in each component separately, right? So here I do a composition in C of F and F prime, and here I do a composition in D of G and G prime. Right. And then for the associativity, well, I can just do this in each component again, right? So I use a Kong of the pairing, and then here I need associativity in C, and here I need associativity in D. And similarly for the identities, I can just do it in each component again. Like that. Okay, so I can make this into a category. And now if I want this thing here to be an adjoint, then I need something which goes the other way, right? And then again, it's a matter of thinking, what could I possibly do here? And the only thing I can think of is, I suppose I could put something constant in one of these components, but I wouldn't really do much, but it's worth exploring perhaps. Or I could duplicate the thing I have and put it in both components, right? So let's see if we can do that. So this means that we should define a functor, which is usually written delta for duplicate, which goes from set to set cross set, right? So delta for duplicate the diagonal or whatever you want. So over here, can define the diagonal functor. And so this works for any category C. So I want a functor from C to C paired with C. Okay, so given an X, I want to put it in both components. Given a function from X to Y, then here I need two copies of a function from X to Y, A and B here. Right, so I can just duplicate the F as well. And then what about the identity? Well, that's true by definition. And what about composition? That's also true by definition. Right. Okay, so now I'm claiming that either first of all is a functor. So let's check that. And then that it's an adjoint to this diagonal. So I wanted the action of either. So we get given a pair, and I wanted this to be A, U plus B. The thing I'm interested in. Okay, so here we are given a pair of functions, and we have to make a function from A plus B to A prime plus B prime. Right. Okay, so we get given an X, and it's of this sum type, so we can pattern match on it. It's either inject 1 or inject 2. If it's inject 1, then I can use my F function to transform it to a project runner B, and then inject that in the first component. X. And if it comes from the second component, then I can use my G to send it again to the second component. Inject it there. Okay, now is this a functor? Okay, here we're proving inequality between functions. So let's use function extensionality. Okay, now I want these things to be equal, and I see that the X here is of a sum type, so I would like to pattern match on it. I'm going to upgrade this to a pattern matching lambda, like that. And then I'm actually going to pattern match on the X, and that's going to make these things reduce. Right, so now that was true, and that was true. Okay, and similarly here, I know that I need to pattern match on the X in order to make this F map reduce. So if I do that, then it becomes easy. Okay, so we have a functor, and let's see now what Agda says it means for this functor to be left adjoint to this. So here we get given an H. And what do we have? Let's actually introduce these. So that X is A, B, is C. Okay, so we are given a function from the sum type, and we have to produce a function from A to C and a function from B to C. So okay, so how can I make a function from A to C? Well, I could take the A and I can inject it on the left here and then use H, right? So that's doing H after inject 1. Externality. H and function composition, not category composition. So the H function composition after inject 2 takes me from B to C by first injecting the B in the second component and then using H. Right. Okay, so if I have a function out of a sum type, then I can make two functions out of the components. And in the other direction, I get given, let's do the same thing here. I get given a pair of functions, f and g, and I have to make something out of the sum type. So look at the x, pattern match on it, and if it's an A, then I can use F, and if it's a B, then I can use B. Right. Okay, so I can define maps in both directions at least. Let's see if they are inverses. So here I get given an H. And here, this is the from function, which only reduces if you pattern match. So we'll have to use function extensionality. And pattern match on it. So use a pattern match on lambda. And if it's in left, then this thing is going to reduce to f of x, and this thing is going to give me an inject 0. So that's the same in both cases. It's going to be the same thing. And here, if we are given f and a g, and then we see that this is just always true, because this is the nice situation, right? Well, we start with these things. Start the right way around. And is it natural? That's just natural. So that's nice. We don't have to think about it. We can just give reference. Okay, so what happened here was that we started with something we knew, and we said, wouldn't it be nice if A, this was a functor, and for that we needed to invent this pair category, and B, wouldn't it be nice if this was an adjunction, so for that we needed to find a functor in the opposite direction, and there was only one we could really think of, this diagonal functor. And then we saw that, in fact, this type gives us exactly what we need for A plus B to be left adjoint to the diagonal. So if we didn't know about some types, then we could start with a diagonal and invent them as a way to make this a left adjoint. Right? So we saw that this was exactly what we needed. And also being a left adjoint describes this more or less uniquely. So we know that there's something canonical about some types, even if we didn't know about logic, where we know that they represent a disjunction. Right? We know that there's something canonical about them because they are left adjoint to diagonal. And we had to prove certain things along the way that are always useful. Right? So the fact that we're looking for an adjunction told us what to prove, which is sometimes helpful, so we don't get lost in all the different things we could possibly prove. It could be helpful for us. But now we can use the adjunction to move back and forth, which is going to be very helpful.